Let's go ahead and take a look at some differentials. So what I've written down so far is I looked at a function. This is just nice, easy quadratic. Y equals 3x squared plus 4x plus 5. I took the derivative and got 6x plus 4, right? The derivative is dy dx. And let's look at a specific value. If x equals 1, then y would equal 12. And the derivative at that point, again, the point 1 comma 12 is equal to 10. This is me plugging x into the derivative. Okay, that's kind of the old stuff. Now let's look at the new stuff, the differential. So I'm going to take the differential of y and get dy, and the differential of this side is 6x plus 4 dx. And again, this is comparing the change in y to the change in x and how those things are related. Okay, so if we do this, and we try to find dy at that moment in time, I'm going to plug in x of 1, that's going to make that 10. Right, and then I'm going to multiply by dx, and I have to give you a dx. Let's say dx is equal to 0.2. Okay, and so if dx is 0.2, then I get a dy of 2. Again, that's approximating the change in y, so we're going to go up 2 if we go over 0.2. And again, that's not the real change. The actual change would literally be a delta y. Okay, and so if I wanted to do that, I could just compare y of 1, which we already said was 12, and y of 1.2, which if you plug 1.2 in here, you get 14.12, which says that delta y, the difference between those two values, is 2.12, and you can see these aren't the same. But remember, dy is using the instantaneous rate of change at 1 and assuming that it's that same rate of change over that whole interval. And it's not. Remember, the derivative is going to be changing. So the derivative at 1 and the derivative at 1.05 and the derivative at 1.1 are all different. And so the growth is a little bit different. But dy and delta y are very similar. And if we make delta x really, 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 really small, then those two values will be identical. Okay, and that's kind of where we're going to eventually go, is that we need a delta x of really, really, really small things to make this happen. Okay, so again, this is approximating the change in a variable rather than a rate. But the change in something can also be viewed as the error in something. Okay, so we can look at, let's say we're in manufacturing and we are manufacturing some sort of steel rod. Okay, and let's say the rod is 10 inches. We'll go centimeters, 10 centimeters plus or minus 0.1, okay? This 0.1 is the error because I'm pretty good at cutting these, or my machine is, but I'm not positive that I can say that every single one is 10, but I can say for sure they're all between 9.9 and 10.1, so I have this error. And again, this is kind of your x value and this is dx. And what I want you to notice, then if x is equal to 10 and dx is equal to 0.1, the ratio dx to x is the percent error, 0.1. So it's 0.1 over 10, which is 0.01, which is a 1% error, meaning 0.1 is 1% of that. So we're going to think of this dx as the error, it's the change in x. And we're going to see how does that propagate. So let's say I'm taking this part, but then I build something with it. It's now a square. And we know that the area of a square is x squared. So what then is dA? What's the change in a based on that change in x? Well, I can take the differential and get dA equals 2x dx. The area of this, well, if x is equal to 10, then the area is equal to 100. But if x is 10 and dx is 0.1, then dA is equal to 2 times 10 times 0.1, which would be 2. Again, this would be square centimeters, and this also would be square centimeters. And if you look at that, that's a 2% error. And you see how the original error propagates? If you mess up or you're not sure on this, and then you're not sure on this and this, then the error actually grows in this case. This error is actually twice as big, and hopefully we'll get eventually to say that this is a one-dimensional thing and a two-dimensional thing and the 2 dimensions multiplied by 2. Because now if I take the same thing and I want to build a cube with it, the volume is x cubed, dv is 3x squared and dx. Our volume based on that x equals 10 would be 1,000 cubic centimeters. dv would be 3 times 10 squared times 0.1, which would be 30 cubic centimeters. And you can see that that's a 3% error because it's got 3 dimensions. And so this original plus or minus error in our length propagates through and becomes a much bigger error in the volume. So if you can only measure this side length to within 1%, you're not going to know the volume up to like say 3%. Okay, so let's do 2 more problems similar to this, thinking about dx and dv and dA is not necessarily the change in, but like the error in the calculation based on some other uncertainty. Okay, so let's do one where we just maybe look at, I don't know, let's look at a sphere maybe. Okay, so if we look at a sphere, we know that a sphere, the volume is 4/3 pi r cubed. Okay, and I'm going to take a measurement of this sphere. So there's my sphere, and I'm going to measure it, and I figure out that the radius of this thing is 4 centimeters. But I'm off by maybe up to 0.1 centimeters, because I'm not sure. Remember, 0.1 centimeters is the same thing as 1 millimeter. I can't really be sure how good I am at measuring this thing, so let's say it's up to a 1 millimeter error. And the question is, what is the volume, and then how much could you possibly be off? Okay, so let's go through that calculation. So the volume is this, and I can take the differential dv and get 4 pi r squared dr. Remember, it's very similar to just taking the derivative of this, except there's a dr. And then I'm going to get 4 pi 4 squared times 0.1. Okay, so then dr is something really close to 20.1 cubic centimeters. The actual volume itself, well, that was 4/3 pi r cubed. And if you figure that out, you get 268.08 cubic centimeters, right? And if we looked at that ratio, how would it compare to this ratio? And hopefully by the previous example, we can show that this is 3% bigger, or the error here is 3%, or 3 times the error that this is, because the volume is r cubed. And again, go ahead and look at that, and you'll get a 3 times the error calculation. Okay, and that would say then the volume, you would quote that as 268.08 plus or minus 20.1 cubic centimeters. That's the approximate error that you know. So you would be able to set an upper bound and a lower bound for the volume based on that. Okay, we'll do one more example in this first part. And let's say we were going outside and we were trying to measure the height of a building. Okay? And let's say we knew that this number was exactly 80 meters. Now, it's not necessarily ever going to be exact, right? There would be some error in measuring that, but let's pretend that this error is 0, or it's so small that it's negligible. And then there's some angle, and we take some protractor and we put a line with a weight on it, and we figure out what that angle is. And we're like, you know what? I think we know that angle is 30 degrees plus or minus 1 degree, right? We're not really sure. The string's a little thick. We're not really sure what degree it's on. Okay, so with that information, I want to figure out what's h. When I say what's h, I want to know what the height is, and I want to know what the error in that height possibly can be. So I want to know what h is and what dh is. So let's go ahead and write an equation that relates theta and h. Tangent of theta is h over 80. Just like over here, if I want a relationship between dr and dv, I got to get a relationship between v and r. Same thing here. I have d theta and theta, and I want h and dh, so I got to write some relationship, and this is the easiest one. So now I'm going to take a differential. So I get secant squared theta times d theta equals dh over 80. Remember, 80 is just a constant. The hardest part on this one is realizing that you cannot be in degrees when you start talking about d theta, Now you can take secant of 30 degrees, just make sure your calculator's in degrees. That's just a number. But d theta, remember our derivative rules are built in radians, so this has to be in radians. It can't be in degrees. Okay, so what you can do here is you can find d theta by taking 1 degree and changing it to radians. So 1 degree to radians. Remember, to go to radians, all you have to do is multiply by pi and divide by 180. So take 1 times pi over 180 and you get pi over 180. So pi over 180 is how many radians, right? That's like 1/60th of a radian is basically 1 degree. Okay, so that's some number you can put on your calculator. And at the end here, you're just plugging in everything. Again, I would write this d theta was pi over 180. I'm going to write that as cosine. And again, if you want your calculator in radian mode, well, then just use pi over 6. If you want it in degree mode, then just go ahead and put in 30. It's not going to matter. This is just a number at this point. So let's say we put it in radians just to make sure. So we're in pi over 6 radians. And then we're going to multiply that left side by 80. And then all that equals dh. So then dh would have equaled 0.785, and that would be in meters. And if you come up here and just use the angle of 30 or pi over 6 and actually find h, you get an h of 46.19. And that would be in meters. And so what you could claim is if you go out and you can measure this angle at 30 degrees plus or minus a degree, then you can know the height is 46.19 meters plus or minus 0.785 meters. Meaning it might be this plus 0.785 or minus 7.8. So you have a range of the height based on the fact that your angle measurement, well, your angle measurement might have been 31 and it might have been 29. And that error propagates through to some error in the height. Okay, this was part 1 of differentials. The second part I'll kind of go through some more, some different applications that are a little more complex.